Hi dear students, welcome to today's online class. Today we begin the fourth module of your fourth semester chemistry complementary course. The module is named as spectroscopy. This is an interdisciplinary area of physics and chemistry, and it has wide applications not only in scientific research but in the medical diagnosis and even in our daily life. Citing a few examples, one of the most common cooking device which we use in our kitchen is microwave oven, which make use of microwave spectroscopy or rotational spectroscopy. Similarly, in the medical diagnosis, the most powerful diagnostic tool, what is called MRI scan, is based on NMR spectroscopy, and so on. As the name indicates, spectroscopy is a measurement using light, and it involves interaction of radiation, that means electromagnetic radiation, with matter or molecule. The most important application of electronic spectroscopy is to elucidate the structure of an unknown compound. Because of that, spectroscopic techniques has become most powerful tool in chemical research, especially in organic synthesis. Now, when you remember the term spectroscopy, your +1 classes will come into your mind. You might have heard about this term spectrum mostly in your discussion of atomic structure, where you learned about hydrogen spectrum, which is one of the atomic spectrum, which is an emission spectrum, and you learn various terms related to spectrum like solar spectrum, line spectrum, continuous spectrum, discontinuous spectrum, etc. And this term spectrum has become so commonly used, and it means arrangement of radiation according to wavelength or frequency. So we will discuss in this class some general concepts related to spectroscopy. In 1 or 2 classes from today, we will be discussing general introduction of spectroscopy, and after that we will enter into 3 specific types of spectroscopy which is coming in our syllabus, that is vibrational or IR spectroscopy, electronic or UV visible spectroscopy, and NMR spectroscopy. These are the 3 types of spectroscopy which we have to discuss in detail. But before we go into detailed discussion of individual spectroscopic techniques, let us discuss about various important basic ideas, concepts which should be familiar to you for understanding this technique. First of all, what is the principle of any types of spectroscopy? As I said, spectroscopy involves interaction of radiation with matter. A radiation, an electromagnetic radiation, may interact with matter or molecules. We take some molecules in this vessel, suppose, and radiation is allowed to fall on it, and this radiation interact with the molecules. Due to that, absorption of certain wavelength takes place. Radiation may get absorbed by the molecule and it can get excited. Sometimes excited molecule get de-excited and emit radiation. So there can be two types of spectrum. One is absorption spectroscopy, the other is emission spectroscopy. Okay, you are familiar with emission spectroscopy in +1 classes. As I told you, hydrogen spectrum, where you excite a sample of hydrogen, so then hydrogen atoms get excited to higher energy levels. The electrons in the ground state go to higher levels, and the excited electron immediately subsequently get de-excited, during which it give out or emit radiation of suitable frequency or wavelength, and you get a series of lines like Lyman, Barber, etc. Also, you are familiar with, in chemistry lab, when you do salt analysis, certain cations give characteristic flame test, like calcium give brick red color, barium give pale green color, etc. What is that? That is also emission spectrum. So calcium give brick red color because the electronic transition in calcium correspond to that particular wavelength. You are familiar with the observation that when copper utensils are used, it may give some flashes of green flashes when it is kept under the flame, strong non-luminous flame. That's also an example for emission spectrum. But these are all atomic spectrum. Hydrogen spectrum, spectrum of calcium, or any other element, these are all atomic spectrum, where emission of light is due to the transition of electrons in the atoms of these elements. But here we are discussing what is called molecular spectroscopy. Our interest is in molecular spectroscopy. Then what is the difference between atomic spectroscopy and molecular spectroscopy? Here in this discussion, we are considering molecules of various substances, and these molecules can undergo transition. A molecule in a lower energy can get excited to a high energy state, during which absorption takes place. So this is mostly absorption spectroscopy. Suppose a molecule is in a ground energy level, say it is E1. Okay, normally molecule will be ground lowest energy state, which is more stable, and this is the excited energy level. If we are giving radiation, molecule in the ground level can go to the higher level. Based on quantum mechanics, it can absorb only this quantum of radiation based on the energy gap delta E. Okay, by Planck's equation, delta is equal to h nu. E is equal to h nu. Energy of a radiation is given by this equation. Okay, or hc by lambda. So since delta is quantized, that means this energy gap can be a fixed value, then frequency or wavelength also will be fixed. So during molecular transition from lower level to higher level, it will absorb only a certain wavelength or frequency that will be characteristic of the molecule. So this gives a wealth of information about the structure of the molecule. Okay. Now in the case of molecular spectroscopy, it is interesting that a molecule can give different types of spectroscopy because a molecule possesses different types of energy. Let's take for example, if you consider carbon dioxide molecule, CO2, you know it is linear molecule, right? Consider carbon dioxide gas kept in a cylinder, right? Okay, there are so many carbon dioxide molecules, and one molecule is like this, according to kinetic theory, molecules are in constant random motion. So carbon dioxide molecules are moving about in straight line, right? So due to, now the question is, what are the different types of energy associated with carbon dioxide molecule? It can have different types of energy, like if it is moving along a straight line, there is translational motion will give it translational kinetic energy. In addition to that, remember that this carbonaceous molecule is rotating about an axis passing through the center, right? CO2 molecule is rotating like this during its movement. So due to rotation, what does the molecule get? What is that called? Rotational kinetic energy, right? And in addition to that, this bond is like a spring, right? It is stretching, it undergoes stretching, means it get extended and contract, extension and contraction. So the carbon dioxide, in carbon dioxide, the two bonds, carbon-oxygen bonds are getting elongated, getting contracted about a mean position. So this is called vibrations, stretching vibrations. It can be symmetric stretching, like both bonds are getting elongated simultaneously, contracted simultaneously like this. It can be also one bond is getting elongated, the other is getting contracted like this, asymmetric stretching. So these are stretching vibrations. Also, suppose this is carbon dioxide with carbon here, oxygen here. The bond angle is 180 degree and this bond angle can vary like this. This is called bending. It can decrease or increase like this. This movement is there. So all these are called vibrations, stretching or bending. In stretching, bond length is changing. In bending, bond angle is changing. Due to these vibrations, molecule will possess vibrational kinetic energy. So molecule is having different types of energy. In addition, in carbon dioxide, there is one carbon and two oxygen molecules, atoms, and in the molecule, according to molecular orbital theory, there are different molecular orbitals, bonding and anti-bonding. Electrons are distributed in various MOs. Okay, so due to the position of electrons in various orbitals, molecule will definitely have electronic energy. So a molecule is possessing different types of energy. So during transition, during spectroscopy, when we allow a radiation to fall on a molecule, the change in energy can be different. That means its vibration energy can change, its rotation energy can change, electronic energy can change. That means transition of molecule can take place between different types of energy levels, like vibrational transition, rotational transition, electronic transition, the magnitude of which will be different. When delta E differs, when energy gap is different, then wavelength absorbed will be different. So there are different types of molecular spectroscopy. Okay, so we will see what are the different types of molecular spectroscopy and what is the radiation used for that transition, etc. in the coming classes. So in this class we discuss, as I told you, in any spectroscopy, electromagnetic radiation, EM radiation, interact with the molecule. Suppose this is a molecule present in the sample. So we have to first discuss about what is the speciality of radiation, EM radiation. We will discuss that. Okay. What is electromagnetic spectrum? What are the properties of radiation? See, during spectroscopy, when electromagnetic radiation interact with molecule, what happens is that, as I told you, there occur transition of molecule. Molecule moves from lower energy to higher energy by absorbing certain wavelength of radiation. Okay, and this transition also is controlled or governed by quantum mechanical selection rule. So in short, we can define spectroscopy as, or it involves transition of a molecule from lower energy level to higher energy level, or it can be from higher level to lower level also, in which case it will be emission spectroscopy. But in molecular spectroscopy, it is mostly of absorption type. So molecule move from lower level energy level to higher energy level by absorbing radiation of suitable frequency or wavelength, and it is governed by, it is governed by quantum mechanical selection rules. What is quantum mechanical selection rules? We will discuss in detail later. the certain restrictions put forward by quantum mechanics for transitions to occur. Okay. Now, let us, so there are two parts for spectroscopy. One is the radiation part and the other is the molecule. Let us first talk about the radiation part, where we will come across what is called electromagnetic spectrum. You are familiar with that. We will represent the major part of electromagnetic spectrum which is required for our purpose. In the middle we always show the visible part, visible range, VIBGYOR. Let me show it like this. In this direction, VIBGYOR, visible part, violet to red. You know, wavelength is more for red, less for violet. After violet comes, you know, it is UV. Okay. And then you have X-ray and gamma ray. X-ray comes, gamma ray, and it is cosmic ray. Cosmic ray. Okay. And radiation having wavelength greater than red, you know, it is IR. Then you have microwave and radio waves having maximum wavelength. See, wavelength is in this direction, wavelength is decreasing and frequency is increasing, you know that. Wavelength of radio wave is as high as 10 raised to 3 kilometers, right? Very large wavelength for radio waves. Not 10 raised to 3, it is 3 kilometers, roughly speaking. Whereas for cosmic ray, it is as small as 3 picometer. When wavelength is large, frequency is small, you know. Frequency of radio wave is 10 raised to 4 hertz, whereas that of cosmic ray is very high, 10 raised to 26 hertz. You know some important equations. The relation between frequency and wavelength, what is it? C is equal to nu lambda, right? C is equal to nu lambda, or nu is equal to C by lambda, you know that. So it's very clear that frequency and wavelength are inversely related, and C is velocity of light. We take it as 3 into 10 raised to 8 meter per second, right? And what is the energy of each radiation? How you calculate using Planck's equation? E is equal to h nu equal hc by lambda equal hc nu bar. Why? 1 by lambda is nu bar, that is wave number. In different spectroscopy, we represent the energy in different units. Sometimes we make use of wavelength as a unit, like nanometer. Sometimes energy of radiation is represented in terms of wave number in centimeter inverse, etc. You can go for a question. You write down a question. Calculate the energy of a radiation having wavelength 400 nanometer. Okay, you can just work it out just to practice this equation. It's very familiar to you. Calculate the energy in kilojoule per mole. You have to find energy in kilojoule per mole. Here you get energy in joules. You know the value of H is 6.63 into 10 raised to minus 34 joule second, right? So when you work out energy, you get energy of one quantum, one photon. You get in joules. To convert it into kilojoule per mole, you can multiply by Avogadro number and divide by 1000. You get energy in kilojoule per mole. Okay, so that's about this electromagnetic spectrum. So there are different radiations having different wavelength or frequency or different energy, and different radiations are used for different spectroscopic technique. Which one we select for each one depends on the energy gap that we'll discuss in coming classes. Okay? Now, you know that electromagnetic spectrum, you know that each radiations, why we call electromagnetic spectrum? Because all these radiations have got two waves which are perpendicular to each other, right? One is an electrical component, right? And there is a perpendicular wave also, that is in a perpendicular direction, that is the magnetic wave. So there are two waves moving, getting propagated in mutually perpendicular plane. One is the magnetic component and the other is electrical component. In other words, every radiation has got two properties, electrical property and magnetic property. So when a radiation interacts with the molecule during spectroscopy, what happens is that one of this wave, either electrical field or electrical wave or magnetic wave, will interact with the molecule, right? Then only absorption takes place. So absorption of radiation takes place only when one of the wave, electrical or magnetic, is able to interact with the molecule. So molecule also should have corresponding pulse, electrical or magnetic pulse. Okay? Then only interaction takes place, absorption takes place, and you get the spectra of a molecule. Right? So that's about electromagnetic radiation. And finally, what about the energy of a molecule? What are the different types of energy possessed by a molecule? I told you about that. For example, in the case of carbon dioxide, I told you carbon dioxide molecule can have 4 different types of energy. Here, so energy of molecule or molecular energy, we'll discuss that now. Molecular energies. So total energy of a molecule can be represented as the sum of translational energy plus then rotational energy plus vibrational energy plus electronic energy. I told you a molecule can have 4 different types of energy. So the total energy is the sum of all these. Okay? And this is given by what is known as Born-Oppenheimer approximation, which says that the total energy of a molecule in gaseous state is the sum of 4 different independent energies. And here, according to quantum mechanics, translation energy is not quantized. In strict terms, if we check, we can see that the translation energy levels are very close and it is continuous, right? It is not quantized. The spacing is so small that it is almost continuous. We neglect translation energy for this part. It is approximately equal to energy of rotational plus energy of vibrational plus energy of electronic. And again, by Born-Oppenheimer approximation, it says that the change in energy of a molecule will be the sum of independent energies. We can represent delta E rotational plus delta E vibrational plus delta E electronic. So the total change in energy of a molecule is the sum of the independent change in rotational, vibrational, electronic energy. All of these are quantized. Now the next question is how we represent these energies. So we can diagrammatically represent all these energies, the single diagram, and see which is more. Magnitude of all these. We can verify which is more and which is less, and then look into the transitions. So in the next class we will represent the energies of a molecule, all these energies in a diagram, and see how the transition takes place. What is the energy gap? Which radiation is useful for electronic transition? Which radiation is useful for vibrational transition? And which is suitable for rotational transition? Giving rise to different spectra in the coming class. Till then, bye.